That's the joint, that's the jam. Turn that up, play it again. That's the joint, that's the jam. Turn that up, play it again.
Hi guys, my name is Nako Nakatsuka. I'm a 4th year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So common monosaccharides have cyclic structures, and now I'm going to show you the formation of 2 cyclic forms of D-glucose. And so this is how you form cyclic monosaccharides from acyclic monosaccharides. So you have a reaction between the aldehyde group at the carbon 1 right here, which is the acyclic D-glucose, and the hydroxyl group at the C5, the ones that are in pink. And they form a hemiacetal linkage, which I'll talk about in a little bit, producing either of 2 isomers, the alpha or the beta, and they differ in the anomeric carbon. And when I talk about what the anomeric carbon is, this is the carbon of the carbonyl in the acyclic form. And this also ends up being the point of attachment to other monosaccharides. And so let's walk through this one more time. We have this group, which is the aldehyde. We have this OH group on the carbon 5. Just imagine this folding over where this is still the carbon 1 and this is the OH group of the carbon 5 to form this 6-membered ring. And so now this OH group forms a bond with this carbon to create alpha D-glucopyranose and beta D-glucopyranose. And as you can see, this carbon right here is the anomeric carbon because it was the carbon that was the carbonyl group right here in the acyclic form. And also, this is going to be the anomeric carbon that is going to form glycosidic bonds with other monosaccharides when creating, for example, disaccharides. So the introversion of alpha to beta is called mutarotation, and they have identical optical properties. And so basically, many acyclic monosaccharides are in equilibrium with more stable cyclic isomers. So as you can see, this arrow goes back and forth, saying that it's at equilibrium with these cyclic monosaccharides. So since this guy is more stable, the acyclic form actually prefers to be like this. Also, when we look at the alpha versus beta, the alpha D-glucopyranose has the OH in an axial position, which is actually less stable. For the beta D-glucopyranose, the OH is actually in an equatorial position, and so it's more stable. Another important thing is the direction of the OH group that's attached to the anomeric carbon, because that affects whether something is alpha or beta. So as you can see, in the alpha case, the OH group is right here, whereas in the beta case, the OH group is right here. And so this affects whether something is alpha or beta, and in general, alpha is when you have equatorial down, or axial down. And beta is when you have equatorial up or axial up. So going back to looking at structures that are cyclic like this, do you remember looking at the chair conformation? When you look at the chair conformation for a 6-carbon ring, remember that you have axial, which are the straight ones going up and down. So I'm going to label all of these as X. And then you have the equatorial bonds that are in a tetrahedral configuration at every carbon, like this. So this is what I'm talking about when we talk about equatorial down versus axial down, equatorial up, axial up. For example, this is considered axial up. This is considered equatorial down. This is equatorial up, and this is axial down. And since we're looking at practically a six-membered ring, right? It's just like the chair conformation. And at every carbon, you can see whether this OH group is on the equatorial down or equatorial up, or axial down or axial up, which will determine whether it's going to be called alpha or beta. One more thing is that if the anomeric group is an OH, then the stereochemistry shifts back and forth from alpha to beta via mutarotation. But if the anomeric group has an OR group, not an OH, then the stereochemistry is fixed as alpha or beta with no rotation. So that's just something to keep in the back of your mind.